Okay, let's look at some problems to review for our quiz on the first three sections of Module 4. So the first thing we did is we just kind of reviewed kind of the definition of log. So remember, log is really asking what is the exponent that I have to raise the base to get the given number in the logarithm. So in this first question, log base 6 of 216, I'm really thinking 6 to what power is 216? Well, in this case, 6 to the third is 216, so the log base 6 of 216 is 3. You can also check these on your calculator, on Desmos, on a TI calculator, however you want to check those just to make sure we're getting the right answer. But all these should work out to be pretty nice answers. Second one says log base 9 of 180 over 81. So it's again asking 9 to what power is 1 over 81. Well, we know 9 squared is 81. 9 times 9 is 81. So we have a 2, but since it is a fraction, remember it's always negative because the negative exponent flips the number to make a fraction. Finally, log base 3 of 243, same idea. 3 to what power is 243? Well, it's just 3 times 3 is 9, so 2 of those. Times another 3 is 27, times another 3 is 81, times another 3 is 243. So there are 5 factors of 3 in 243. So the other big thing we did in the first section is we talked about how to solve exponential equations using the exponential law. So the exponential law, recall, said if we had b to some power on one side and b to some power on the other side, then we know that the two exponents are equal, x equal y. Same idea here. Now in this first one we see that we have bases of 1/3 and 27. Those are not the same. So I'm going to try to change those to be common bases. So we have 3 and 27, so I'm going to assume the common base I'm going to aim for is going to be 3. Now in the first one I have 1/3, so the only thing I really have to do is flip it, so I can just put to the -1. So we have 3 to the -1, and then the 2x plus 1, which was the previous exponent, make sure it is in parentheses. So now we'll try to change 27 to have a base of 3, which if you remember 27 is just 9 times 3, so it's basically 3 3s. So 3 to the third times 2x plus 1. So now those have the same basis, so we could just set the exponents equal. Very important to make sure you put those parentheses, though. Without those parentheses, you might miss distributing in the next step. Because we're going to distribute the -1, we're going to distribute the 3. So that's negative 2x minus 1 equals 6x plus 3. I'm going to get all the x's on one side, so I'm going to add 2x. And I'm going to subtract 3. So that's going to give me negative 4 equals 8x. And so I'll simply divide by 8. So x is going to equal negative 1/2. Well, the next one next to it is very similar. Well, we'll try to get the bases the same, although this one's a quadratic because it has the x squared. So we have 2 on one side and 16 on the other side, so we really can't change 2 to too much, so I'm going to just keep it as 2. And so we'll try to see if 16 is a power of 2, and it is. It is 2 to the 4th. So now we have those. We have these two exponents equal. We could simply set them equal. X squared equal 3x equal 4. And now since it's a quadratic, we'll get everything on one side. X squared minus 3x minus 4 equals 0. So now if you want, you could solve by factoring, quadratic formula, completing the square, any of the methods to solve a quadratic. This one does factor, so I'd certainly do that. But if it doesn't factor, you could use one of the other methods. So negative 4 and positive 1 are two numbers that multiply to negative 4, add to negative 3. And so if we set those equal, we get 4 and negative 1. Okay, the other thing we did in this couple sections is we were really graphing the exponential and the logarithmic functions. So we'll look at doing that. So this first one we have f of x equals 3 to the x minus 6 minus 9. So we want to know about the y-intercept, the asymptote, and things like that. So the y-intercept, remember, is just simply f of 0. So in this case, that's simply going to be 3 to the minus 6 minus 9. So if we're figuring out what this is going to be 1 over 3 to the 6 minus 9. So it's going to be something really, really close to negative 9. So we'll just approximate it in this case. We'll say it's negative 8.99. Yeah, pretty close to that value. So we have basically 0 and negative 9. Now the asymptote is always the shift down, so it's always our k value, which in our case is negative 9. Always horizontal, so this should have a horizontal asymptote of negative 9. Domain and range. For exponential, the domain is always infinite. So for every exponential, always has negative infinity to infinity. The range, since this one is not flipped, it just kind of goes up. It's going to go something like this. It's always from the asymptote to infinity, and that's only if it is not flipped over with the negative in front of the base. Transformations that occurred, a couple transformations. So if we have the 3 to the x minus 6 minus 9, then I know the minus 6 is going to shift it right 6. Because remember, it's always the opposite for the horizontal shift. And it's going to shift down 9. And that'll help us get a graph of this thing. So for now, I'm going to skip the inverse. We'll come back to that. Let's go ahead and plot this, and then we'll find the inverse of this exponential function. So if I go down here, it says plot the some points of 3 to the x, and then use the transformation to draw this graph. Now, can you draw this on Desmos? Absolutely. But we want to try to actually show the movement of this graph. So if I think of y equal 3 to the x, I could put some points on there, and I'll put it in this black color. So negative 1, 0, 1, 2. So this would be 1/3, it'd be 1, it'd be 3, and it would be 9. And that's simply plugging the x's into 3 to that power. 3 squared is 9, 3 to the 1 is 3, 3 to the 0 is 1, 3 to the negative 1 is 1/3. So if I plot those, it's going to look something like this. And the traditional exponential has its intercept right there. So all I'm going to do in my transform function is I'm going to move it right 6, and I'm going to move it down 9. So if I want to think about this graph, if I actually want to write the points, I'm going to move all the x's right 6. So I'm essentially going to add 6 to all these x's. And I'm going to move all the y's down 9, so I'm going to subtract 9 to all those y's. So if I want to draw it out, that's going to become 5, 6, 7, and 8, just by adding the 6. Now subtracting 9 to some of these will be pretty tricky. So this would be negative 8 and 2/3. So then we do 1 minus 9, that's going to give me negative 8. 7 minus 9, or I'm sorry, 3 minus 9 is going to give me negative 6, and then 9 minus 9 is going to give me 0. So now we'll go ahead and plot these. So we have 5, negative 8, and 2/3. Now remember, we have a horizontal asymptote at negative 9, so that's where this graph should kind of approach. So over 5 down to 8 and 2/3 is going to give us a point there. Over 6 and down 8 will give us a point like there. Over 7 and down 6 will give us a point there. And over 8, 0 is there. So if I plot the graph, connecting those points, kind of see something like this. So just by doing this, you can kind of see the graph has been moved right and moved down to kind of get our new graph. Now let's go back up here and talk about its inverse. Now the inverse of every exponential is going to have something to do with log, so this one is no different. So if I think of this function, y equals 3 to the x minus 6 minus 9, remember the idea in finding an inverse is we're going to switch the x and y. So x equals y minus 6 minus 9, and now we're going to get the exponential by itself and switch to log. So I'll go ahead and add 9, because the whole goal is to get 3 to some power equal to some other stuff. So we get x plus 9 equal 3 to the y minus 6. Now the way to get the exponent down and by itself is to switch to log. So we put y minus 6 by itself, log base 3 of x plus 9. And now real simple to get y by itself, I'll just add 6. So my final inverse function is going to be y equals log base 3 x plus 9 minus 6. Plus 6, pardon. All right, let's look at one example where we're talking about a log function. So we're going to look at log base 4 of x minus 2. So again, we're going to really rely a little bit on the graph of the function. I have it pulled up on Desmos. You should as well. So x-intercept is simply going to be 3, 0. If I want to do it algebraically, a little tricky, remember we put 0 in for y. So it would be 0 equals log base 4 of x minus 2. And then I'd simply switch to exponential form, which is 4 to the 0 equals x minus 2. But 4 to the 0 is 1, so it's 1 equals x minus 2, so x is 3. Now again, I just looked on the graph, not too tricky to find it there, but that would be the algebraic computation. What is the asymptote of the function? It is a log function, so it has a vertical asymptote. And since we can see inside the function it's got the minus 2, which I can say right away is the transformation is shifted to the right by 2. So when we shift it right 2, that's going to make that asymptote x equal 2. Remember, whatever that shift is going to be your asymptote as well as your points. So domain and range, remember the range for every logarithmic function is always negative infinity to infinity. And the domain, since we're moving the asymptote to the right, is just going to be that asymptote and bigger, so 2 to infinity. So let's go ahead and graph it, and then we'll come back and do the inverse function. So as you remember from the notes, there were 2 big points you want to graph on every normal log graph, and that's 1, 0, and b1. So in our original function, we're trying to graph f of x equal log base 4 of x. Well, I know 2 points on there are going to be 1, 0, and 4, 1. 1, 0, 4, 1, and then we'll have a asymptote at 0. So my original function looks something like this. Now the only thing I'm doing for my new function is I'm going to shift it right 2. So when I look at f of x equal log base 4 of x plus x minus 2, that's shifting it right 2. So all I'm really doing is I'm adding 2 to all the x's. So for those 2 points, it's going to become 3, 0, and 6, 1. The other thing I know is we have this asymptote at 2 now, because that got moved over by 2. So there's my new asymptote. So my intercept 3, 0, which I knew from before, and 6, 1 is my new point. So this new graph is going to look something like this. So you can see the red got moved over 2 to get our graph. Now for inverse, we're just going to do the same thing we did for exponential. So since we have y equals log base 4 of x minus 2, we'll first switch x and y. So this will make it x log base 4 of y minus 2. Now there's nothing to move over right now because all the stuff is in the log. There's nothing in front of the log. So I can just go ahead and switch to exponential form. So that's y minus 2 equals 4 to the x. Real simple to solve from here. I just simply add 2 to both sides. So the inverse function is going to be y equals 4 to the x plus 2. So I would encourage you to make sure you're looking at Desmos, graphing these parts of the graph, so you can really see how they all work in this problem.